Hey, welcome. So my name is Andrew Liu. I'm a PM on the Azure Cosmos DB team, and today we're going to talk a little bit about Azure Cosmos DB. So let me switch over to the right computer. Cool. Awesome. So you guys have made it through the maze to get over here. Congratulations. I promise you this session will be worthwhile. So today, what we'll do is we'll talk a little bit about Azure Cosmos DB, some of the core concepts. I'll give you kind of a quick TLDR, like in case you're new to the service, what the heck is this thing? And then we'll talk about the core concepts around the resource model, the request units, partitioning, replication, automatic indexing, and then we'll talk a little bit about some of the cool new things that we have available for build. So first, what is this thing? In a nutshell, Cosmos DB does three core things very, very well. That's partitioning, replication, and resource governance. The partitioning allows us to give you the elastic scale-out of storage and throughput. So you can have something that's very small and grow it elastically, seamlessly to something very large. And the replication allows us to deliver turnkey global distribution to replicate that data to any number of regions, along with a tunable consistency model so that you can manage the right trade-offs between performance with respect to consistency. The resource governance allows us to give you SLAs beyond just high availability. So Cosmos DB can offer 4 nines of availability in a single region, 5 nines of availability through multi-region. However, availability is just one aspect of a database. What you also care about is the performance. Is it possible to achieve predictable performance? And so what we've done is we've implemented resource governance at a very fine granularity at a per request basis. And what that in turn allows us to do is give you very novel, unique capabilities like guaranteeing the throughput that you've provisioned, as well as the latency for each individual request. On top of this core platform, we've built this as a schema-agnostic data store, and we're able to efficiently project 4 different non-relational data models on top of this. That would be the key value column family document and graph data models, and these can then be exposed through a variety of different APIs, ranging from a tables API, a Cassandra API. We have our own dialect of SQL, MongoDB, and Gremlin, where Gremlin's kind of the oddball out of here, but it's really cool. What you can do is you can do also graph traversals on top of Cosmos DB. So now that you have an idea of what is this thing, let's talk about how you take advantage of it. What are the core things that you need to know? The very first thing to understand is going to be the resource model. So as you provision a Cosmos DB account, the very first thing that you'll be presented is an account. The account is just a URI and an endpoint for connecting your client application to Cosmos DB. And setting this up is extremely simple. So what we do is we go to the portal.azure.com, click on databases, go to Cosmos DB, name it, choose an API, choose an Azure subscription and a resource group, starting location, click create, and you're up and running. 5 minutes, you're up and running. You're not spending a week, setting up VMs or anything like that. Once you have your account provisioned, you can provision a database. A database will have a set of containers, and those containers in turn will store your data. What's interesting about the containers is that we, depending on the different data models, we'll project them differently. So if you're coming in through a document-oriented data model, we'll likely call this container a collection. Meanwhile, if you're using our Gremlin API, this is a graph, and if you use our tables API, this is a table. Underneath a collection, here's where things get interesting. This is where the first time you're going to see physical resources likely. We give you unlimited storage through the elastic scale-out, and we also ask you to provision an amount of throughput. That throughput you can scale up and down on demand, and we can basically attach and deploy this container across n number of partition sets underneath. The magic that makes this happen is you're going to define a partition key, and that's going to be a logical hint for how you want to distribute the data onto the underlying partition sets. And we'll talk a little bit more about that in just a second. Once you've provisioned the container, you can store your data, of course. We call these items to be data model agnostic, but these would be your documents, your rows, as well as your vertices and edges. We also feature a server-side programmability model in which you can implement store procedures and triggers This is going to be your mechanism for performing multi-record transactions. So a little bit different from other distributed databases. It turns out distributed transactions are very difficult. And what you end up having to do is do a two-phase commit, and there's some trade-offs with respect to how you manage conflicts and concurrency. A lot of distributed databases will steer you towards doing transaction over a single record at a time. Cosmos DB brings multi-record transactions back on the table through the use of stored procedures and triggers, with the caveat that you must scope this to a partition key. We also have a user-defined function model for extending our query language. And then, of course, in our resource model, the last thing to know is conflicts. Conflicts are both interesting from a perspective of we guarantee the durability of all your data. We don't play any tricks like some of the other databases where they'll buffer things in memory before acknowledging a write. Instead, every time you make a write operation into Cosmos DB, when you say and acknowledge, we have durably committed that write to a quorum of replicas. Now, then what is this conflict feed? Well, for one, we support multi-region deployments. And so when you do automatic failover from one region to another, there's going to be a slight window, a trailing window of about tens to about a few hundred milliseconds, depending on the distance of the two regions. That is because we also, like you, follow the laws of physics. It turns out you can't send packets faster than the speed of light. And so we actually have metrics where we'll expose probabilistic probabilistic bounded staleness of how we've propagated the data to replicas across different regions. Should we ever have to do an automatic failover due to a natural disaster or whatever, we guarantee the durability of that data, but should you have written that data to another data center, we can expose these to the conflicts feed. We can also expose conflicts for the multi-master support, which I'll talk a little bit about later in this session. So that's kind of the user-facing resource model. What does this look like behind the scenes? Behind the scenes, this is a globally distributed database, and we like to start with Planet Earth. In Planet Earth, we have roughly 40 Azure regions today. It keeps growing day by day, and I've lost track personally. But we have a ton of Azure regions, and in these Azure regions, we build data centers. As we build these data centers, we deploy these big racks that we like to call stamps, and we divide them into fault domains. These fault domains, of course, have a shared set of infrastructure, and so if we deploy a cluster of several hundred machines across tens of different fault domains, what we can do here is deploy a replica set across multiple fault domains to give you something that's highly resilient even to hardware failures. So within this cluster of hundreds of machines, this is where the magic happens. Within those machines, we host database replicas. The database replicas are going to be the core building block for Cosmos DB. And within that, we're going to have our resource governor for giving your throughput and latency SLAs. We have a transport layer for doing replication, admission control for authentication and authorization, and of course, our bread and butter, the database engine, where we do all of our query and indexing. So within each of these containers, we have these partition sets that are composed of database replicas. And what we do is we host 4 replicas per region. And the reason why we have 4 is this way we can actually offer you extremely high availability where we can deploy database updates, we can deploy operating system updates, hardware updates, completely transparent to you. The mechanism that this works is every time you do a write operation, a read operation, what we'll do is we'll rely on a quorum mechanism. It's a dynamic quorum where we can look for 3 out of 4, or whenever we want to pull out a replica, apply an OS update or database software update, we can dynamically size that quorum to 2 out of 3. By the fact that still always having at least 3 when we pluck one out of this replica set, what that means is that these database updates or software updates are completely transparent to you, and you can still lose a replica because we have a quorum at any given time while not affecting availability. The gist is this database was always online. You don't have to worry about hardware updates. You don't have to worry about software updates. We're always available, always online. So now that I have kind of an idea of the topology of what the resource model looks like, let's take a look at one of the very important concepts, which is request units. At first, I think a lot of people, when they first time they dive into request units, it's a little bit of a confusing subject, but I promise you it's actually something that's really awesome. And here's why. The request unit, first what it is what we've done is we've normalized all of the physical resources it takes to process a request, the CPU, the memory, the I/O, across a single dimension. That way, when you're scaling your application, How many of you guys have done capacity planning for your database before? How many of you guys actually find this is a fun exercise? Whoa, there's like two of you guys. Awesome. So the thing about capacity planning is it's really tough, right? Especially when you're deploying on-premise. You have CPU, you have memory, you have I/O, and your boss comes to you and says, hey, I need you to scale from 1,000 requests per second to 2,000 requests per second, because that's what our forecast tells us. And you go, do I add more memory? Do I add more CPU? How many gigabytes of RAM is how many requests per second? I don't really know. So what you end up doing is you do all this like benchmarking and stress testing, figure out what the bottleneck is, play whack-a-mole, relieve that bottleneck. Maybe it's memory, and then suddenly a new bottleneck shows up, right? Well, we can do something much better than that, and that's why request unit exists. What we do is we do a logical charge on all of the, we use machine learning to produce a logical charge for every request in terms of request units. And then what we do is we make sure that's stable. So if a request, let's say, takes 5 request units today, our promise to you is that's predictable. It should take 5 request units tomorrow, the day after, and no more than that in the future. And so if you need to do, let's say, 1,000 operations per second, and you know that these operations cost 5 request units each, 5 times 1,000 is 5,000 request units per second. Should you now need to raise to 2,000 operations per second, 5 times 2,000 is 10,000 request units per second. Your capacity planning is literally mental math at this point. So we've made that really easy. All you have to do is really understand what a request unit is. Now, why we use request units and not requests is because it turns out every request is a little bit different. When you do a read request, while we can guarantee that the same follow-up read request is a stable, predictable charge, it turns out that a read, we can actually go to a single replica, pull out a value, and return, depending on the consistency level. Whereas a write, of course, we're going to have to replicate to all of our replicas and generate those index entries. And so what we do is we normalize all of this into request units. And you can think of this as just how many CPU, memory, and I/O a particular request takes. Our model is, you can think of as a token bag model. What you're doing is you're provisioning a token bag full of request units. Every time you perform a request, we take some tokens out of that bag. Every second, we go and replenish that bag. If you exhaust that bag, then what we do is we'll just instruct the client, hey, hold on. We try the request a second later. So if you have bursty spikes in your workload, what you can do is you can actually use this rate limiting to amortize the cost those requests over time. Or what you can do is you can actually increase and decrease these request units on demand. And that's what's really powerful about this being a cloud system is you only have to pay for what you need. You can actually increase and decrease how much RU per second you have provisioned at any given time. We meter these hourly, so if you have a workload that's hot from, let's say, hours 9 to 5, increase your RUs from 9 to 5, and decrease your RUs after that. We also do make sure to use any leftover RUs. We do have some background processes, like you can set data retention policies right out of the box with our time to live feature, as well as doing things like index transformations and other kind of background tasks. We can take advantage of those leftover RUs. So one of the new things at Build that we're releasing is previously you would provision these request units per second at a particular container. This is great when you have a greenfield application and you can design around co-locating, let's say, different entities across a single container. However, sometimes what you're doing is you're taking advantage of, let's say, our MongoDB API, our Cassandra API, and what you find is that that existing piece of software actually treated containers as a logical namespace and provisions a lot of these. And so now with provisioning RUs for a set of containers, what we allow you to do is set the request units at the parent database or key space. And that way, a set of containers can share that RUs per second. They'll be co-located on the exact same cluster. Now, request units are, you can love them, you can hate them, but let's talk about something a little bit more interesting now, and that's scale out. How do we actually scale out in Cosmos DB? So one of the really cool things about Cosmos DB is you can start small, grow large, or you can go from day one, put an extremely large workload, whether that's hundreds of terabytes or millions of requests. It really doesn't matter. The key that makes this happen is each instance is tied to a cluster of machines that we can dynamically size. Now, we can have that cluster small, we can have that cluster large. So how does this actually happen behind the scenes? Well, remember in the resource model, we talked about this concept of a partition key. You're going to go and give us a hint on how do you want to distribute your storage and your requests onto underlying storage nodes. So what we do behind the scenes is a technique called consistent hashing. And what we're doing is we're taking those partition key values, we hash them to get a nice pseudo-random distribution. That way, if you have, let's say, an incremental user ID, you're not front-loading them all to a single partition. Once we now have this distribution, we map them to underlying storage nodes based off your actual storage and throughput needs. That way, if you have a billion partition key values, you don't have to actually spin up a billion physical partition sets, because that would be really expensive. So what we do is we actually look at your storage and throughput needs and size this down, and we'll co-locate many of these logical partitions, these partition keys, on a fewer set of physical partitions. Now, the really nice thing about consistent hashing is what happens when you want to dynamically grow or shrink this, this cluster. Let's say this partition on the end here, the fourth one here, is growing and it's starting to fill up. Well, what we can do is monitor this ahead of time and do what's called a split. And what we'll do is for that range of values, Dharma, Sharish, Karthik, Rima, Alice, and Carol, well, we can give them double the storage and double the throughput by splitting them up such that half the partition key values go to one partition and the other half go to another partition. The really cool thing about this is we're not giving you tooling to give you elastic scale. We're actually managing all of this for you. So we proactively monitor each of your collections and the underlying partitions. And what we'll do is we'll proactively grow the number of partitions. That way, from the application's perspective, you now have a database that just elastically and seamlessly grows as your application grows. Now, we have done 95% of the work in terms of sharding, which is all of the operational costs of how do you route requests, how do you route the data, as well as how do you grow and shrink this cluster. But that means we haven't done everything yet, and that's the remaining like 5%, and that's just a design time decision. For the remaining 5%, this is your exercise of just choosing a good partition key. What is a good partition key? Well, at a high level, what you do is you have two different design goals. The first design goal is you want to distribute the overall request and storage volume so that you avoid hot partition keys. So let me give you an example. Let's say you have an IoT scenario where you're storing device telemetry. Intuitively, a lot of people might first go to, let's say, a time dimension, like the current time, because that'll give you a very even distribution of that data across many partition keys. However, what I want to point out is you also want to distribute your overall request volume. And so at any given time, all of those requests coming from all of these different devices actually will have the exact same current time value. And so what will happen is all these requests will get routed to that first partition or one partition, leaving everything idle. Instead, what you want to do is you want to distribute the throughput as well. And so a common technique for IoT telemetry is to choose, let's say, the device ID as the partition key. The device ID will give you both a even distribution over storage as well as over the request volume, as well as it turns out most of your queries will likely be on a particular device as well. That brings us to the second design goal. The second design goal here is you want to choose a partition key that allows you to scope your queries. Our SDKs are intelligent. They actually ship with a query parser as part of the SDK. And what it'll do is it'll pull out the partition key value and say, hey, you're running a query that says select star from this collection where partition key equals ABC. I know that ABC hashes to, let's say, 123. 123 is on partition 5. Let me go and ask partition 5 right away for that piece of data. In the absence of a partition key, what happens is called a fan out. In a fan out, what we do is we just ask all of the partitions in parallel. And because this can be heavily parallelized, your hit on latency is minimal. However, if this is something that happens with very, very high concurrency, over time, this is not the most efficient thing you want to do. And that way, what you want to do is you want to choose a partition key that ideally allows you to scope that query for the bulk of your queries. So here's what you're going to do. You're going to first ballpark your scale needs. And you're going to get an idea of, do I have tens of gigabytes? Do I have hundreds of terabytes? And that'll allow me to actually make a conscious decision on how much do I even care about fan out. At the end of the day, if I only have 10 gigabytes of data, this really not need to be a concern. Once I understand that, the next thing you'll want to do is understand the workload. Is it read heavy? Is it write heavy? And what you want to do is you want to operate off of Pareto principle, the 80-20 rule, because at the end of the day, it's very easy to get into analysis paralysis where you can go, what if I want to do this? What if I want to do that? And then you spend the next years thinking of what ifs. But what you are forgetting is a lot of these what ifs are really edge cases that happen once every now and then. It's totally OK to fan out. for those edge cases. What you want to do is you want to make sure that the partition key design is actually appropriate for the bulk of your workload. So for a read-heavy workload, what you want to do is you want to look at your top 3 or top 5 queries, look at the where clause, and choose commonalities out of the where clause. For a write-heavy workload, the main thing to think about, in addition to distributing the overall request volume, is understanding transactional needs. At the end of the day, we do give you multi-record transactions scoped at the partition key level. Some general tips here. A lot of people do fall into this analysis paralysis trap the very first time. Try to avoid that. Actually, the best thing to do is build a proof of concept. Once you build a proof of concept, it'll become very crystal clear exactly what might be a good partition key for your application. The other thing is, don't be afraid of having too many partition keys. I get so many countless questions going, hey, you know, I'm building, let's say, this big, massive social media platform. I might have to support billions of users. Is that too many partition keys? The answer is no. In fact, the higher the cardinality of the partition key, the better. If at the end of the day you only have one partition key value, we can only distribute that across a single physical partition. However, if you have billions of partition key values, logical partitions, we can start small, co-locate them on a single partition, and grow that elastically into a billion different physical partitions. So with that said, I'd like to invite my colleague Ram here. He's going to also tell you a little bit about some new awesome things that we are working on. We have a bulk executor library to make high throughput applications even easier.
Thanks for that, Andrew. Right. So hope you guys have been having a good build so far. So as Andrew was saying, right, Azure Cosmos DB is a really flexible database service, which provides it gives you the opportunity to scale up to really large read and write workloads. And that's essentially what we call elastic scale-out. And that also allows you to store petabytes of data, which you can then operate on with millisecond latency. And all of this is very, very predictable, right? Now, this gives you a lot. So the service itself gives you a lot of potential, which you want to basically exploit on the client side. And that's where the bulk executor library, which we are now GAing, comes in. So what is the bulk executor library? It's nothing but it's an extension library to our core SDK, which allows you to perform bulk operations on Cosmos DB via APIs, which we now support for bulk import, bulk update, bulk delete. And I'll go into further details about that. And when we're GAing it in both .NET and Java. So that said, let me So it's not that you could not perform bulk operations earlier on Cosmos DB, right? So what was it that you could do? Earlier, developers used to write multi-threaded applications, which would then interact with Cosmos DB. And each of these threads in such a multi-threaded application would use our core SDK to perform point operations. So for example, if you're doing bulk import, you would use point requests to basically write documents. Now there's a lot of overhead when you're using the core SDK for such a purpose. Now the core SDK, as you know, we have an SLA that at the 99th percentile of all your requests, the write requests will take less than 15 milliseconds. So that's really good. But what if you're trying to migrate, say, a terabyte of data, so with more than millions of such requests? Now, there's a lot of overhead if you were to individually send such requests and then get an ACK from the service. Now, when you're doing this, you also have issues of how do I handle rate limiting. So as Andrew was mentioning, we have this concept of request units, right? Now, say at a specific time, your load on the service is too much. So automatically, the service will give you a status code saying you've exceeded the current throughput you've allocated to your collection. So the earlier developers would need to write custom logic to handle such rate limiting feedback, as well as request timeouts, or any other interaction with a cloud service, right? Now, all of that is currently inherently handled under the hood inside the bulk executor library. So it is really, really simple for developers right now to leverage this and perform bulk operations on Cosmos DB. So we've been in preview for a few months now with the bulk executor library, and we have a lot of customers who are already in production who are basically using the library to both import and update terabytes of data every hour. And these are services which basically do this every hour in production. So let me just put that back into action, right? So let's do this. Like, I have a nice demo here which compares and shows you the difference between performing such a bulk operation using the core SDK versus the bulk executor library. Right. So I'm sure if you we have does it not? Right. So we have this is our official GitHub page, which has a lot of samples, which you can, if you have not already checked it out. So one such sample is a performance benchmark, which we earlier published, which essentially is a sample which spawns multiple threads to basically migrate data into Cosmos DB. So essentially, one of the on this demo, we will be benchmarking against this sample here. And the other is also, with today, we have documentation and samples out for the bulk executor library as well. So again, this is publicly available on GitHub. And that's the same import sample which we'll be comparing against. So what this performance workload here does is we will be generating the same set of documents in both the samples, and then ingesting using the two different processes. So one, we will be spawning multiple threads and using the SDK, and the other will be a single thread which calls the bulk import API. So let's just compare the two here. OK, so as you can see here, I have a Cosmos DB account which I've already created, and just for the sake of this demo, I've also created a collection here. Now, as you can see, I've created this collection with 50,000 RUPS. So this is not a really large collection in the scheme of things, right? This is a pretty medium-sized collection. Now, let's do one thing. First, so let's use. Oh, OK. How can I screen it up?
Here, can everyone see the text here? We're zooming in a little.
Right. So this is the sample which writes data using the SDK, right? Now, I'll just to show you what I'm doing here is I'm essentially going to be creating 50,000 documents and then ingesting that to the collection which I just showed here. So let's see what happens there. So here, what it does is, as you can see, it spawns 2,000 threads on this Azure VM here. It's a 16-core VM. And as you can see here, you're being So OK, this is a very nice example of what happens here, right? Now, as you can see here, there are exceptions which are getting returned to you. And as a developer, you would have to write custom logic to catch these exceptions and then handle them. But as you can see here, let's yeah, so you can see here that you were able to write the 50,000 documents along with, and then some of the documents also threw exceptions here. But it took 37 seconds to complete this. Now let's go to another example where let's go to one order of magnitude higher, where so you had a collection with 50,000 RUPS. Now say you want to, the load on your service is going to increase 10x. So I would go to the portal and essentially scale that up by another 10x. So I would go here and basically, right now I have a 50,000 RUPS. Now I scale it up to 500,000 RUPS. Right. So as you can see here, we've scaled that collection up to 500,000 RUPS, right? Now let's go back to the config here. And now I'm trying to, say, import 500,000 documents into that collection here. So now if you can. So in the same scenario here, you can see now that although I have created the collection with 500,000 RUPS, just give that. I just have these exceptions being thrown to showcase that in this demo, but let that. Yeah. So but you can see here, right? So essentially, you're consuming only 36,000 RUPS out of the entire 500,000 RUPS you've created here. So what you would rather want to do is, so let me show you the other PowerShell sample. Right. So this is the other sample which consumes the bulk executor library. And so essentially, this one points again to the same collection which we had there. And here again, it's trying to import 500,000 documents, the same 500,000 documents. And let's see. And as you can see here on the client side, it's consuming the this is basically becoming a live debugging session. We have to see what's happening here. But right. So while that happens, right? So I can, while the import completes, let me just go back to the presentation here. So what does the bulk executor library as such provide? It basically heavily reduces the client-side compute resources you would need to saturate your collections throughput. So compared to the point write sample, the bulk executor library, a single thread consuming the bulk API can write data with 10x greater write throughput. And it also abstracts away all the tedious tasks of you having to write logic to handle rate limiting, request timeouts, and other transient exceptions which you get from Cosmos DB. So essentially, one single bulk executor on an individual VM can consume more than 500,000 RUPS. And so imagine if you had a collection with north of 1 million or 2 million RUPS. All you would have to do was now spin up 2 or 3 of these VMs with the bulk executor library running on them, and you would be able to saturate the throughput of the collection. Versus in previous scenarios, you would have to spin 20 to 30 such VMs. And so far, we've been talking a lot about the bulk import, but we also provide the ability to bulk update existing data in collection using patches. And you can read more about the documentation and samples we have online. We also have something in preview, which is the ability to bulk delete data in a collection by specifying a SQL query. So as I said, all of this is now available in both .NET and Java. And then we also have support for our Mongo API as well as our Graph API in preview. And in the coming few months, we will also make that GA. Another interesting thing is we have native integration into both our Spark connector as well as, so most of you must be aware of Azure Data Factory, which is a very nice ETL, which is a very nice mechanism to basically perform ETL jobs. And now this library has been onboarded onto the ADF connector. So essentially, it brings all these 10x greater write throughput and a transient fault handling and all of this out of the box for all your workloads now. So I'm really happy to for you guys to go out and start testing this out. Yeah, thanks.
Cool. So check out the new bulk executor library. It'll make bulk import, bulk update a lot easier. We have a nice library where you don't have to spin up all these different threads and do point insertions. They become nice, easy, single method calls. So let's now jump over to the other side of distributed databases. We've talked a lot about partitioning. Let's also talk about replication. So partitioning is all about taking a data set and dividing it up, different data across different machines. Replication is all about then copying same piece of data across multiple machines as well. So why is this interesting? Number one is that this is our means of providing high availability. So Cosmos DB does provide both automatic and manual failover across different geographic regions, as well as it manages all of the replicas within local regions on behalf of the developer. We expose all of these different replicas through a multi-homing API, so you don't have to deal with managing addresses or URIs for different regional endpoints. Instead, this is all under a single global URI, and so should you ever need to trigger a failover, Cosmos DB will automatically route requests from one region to another region seamlessly and automatically. You don't have to do any kind of app redeployment or app restart. Beyond just high availability, the other thing that makes this interesting is providing low latency. Basically, packets can't move faster than the speed of light. So how do we actually go around and get around the speed of light is we proactively ship the data closer to where our users are. Basically, what we're doing is we're bringing CDN-like capabilities, except instead of doing this for static content and relying on caching mechanisms, what we're doing is we're providing CDN-like capabilities for dynamically indexed content for a database workload. Now, what this looks like behind the scenes is we have a container which is then further divided into partition sets. These partition sets then hold replica sets, and there's going to be 4 replicas per region. And so up top here, I have a container. I have a partition key, let's say airport. I've divided them across different airports. And then what you see here is we're setting up replica sets dynamically to additional geographic regions. Setting this up is incredibly easy. Here I have a screenshot of our Azure portal. You're not spending, let's say, the next few weeks installing another set of VMs across different geographic regions. Instead, as simple as what we do is we call this turnkey, meaning this is as easy as turning the key in the ignition. I click a few buttons on which regions I want across different Azure regions, and then I click Save, and I'm done. Now, while this is really easy, I do also want to point out for folks who are then going, oh, maybe this is a little too easy, is we do respect geofencing laws and regulations. So you don't have to worry about if you are working in a sovereign cloud, something like, let's say, a Department of Defense or Germany or Chinese region. We also do respect geofencing rules, which we can apply at the subscription level and make sure that data from a single sovereign cloud will not leave that sovereign cloud. But in the for the regions that are outside the sovereign cloud, for which we have about 30 or so regions, you can set up these massive database deployments geographically dispersed across all of these different continents. And so basically what's happening here is if I have an application that previously was talking to a database endpoint halfway around the world, even under ideal network conditions, what you'll see is you'll get about 180 milliseconds to go from West US to Australia. by geo-replicating that data closer to where the application instance is, I can now achieve single-digit millisecond latencies no matter where the user in the application exists. So for automatic failover, turning this on is as simple as toggling a switch from off to on. We allow you to dynamically configure a priority list of regions to failover through. This is a simple drag and drop interface. And then from here, we also allow you to configure this at an individual client level. So if you have individual application instances dispersed throughout the world, let's say one application instance is homed in Central US, another is in Southeast Asia, and another is in North Europe, the overall topology of your application would then be user makes a request, it goes to Traffic Manager. Traffic Manager routes that request to the closest Azure region, and it goes into the application instance. That particular application instance will set a preferred location based off of an application config, where it's aware of which region it's deployed in, and then it'll dynamically configure not just the first priority region, but also dynamically prioritize second priority, third priority, based off of what's closest to it. That way, at the client level, we can also override the failover behavior. In addition to automatic failover, we can also do manual failovers, should you want to do business continuity, disaster recovery drills. And we back this with 5 well-defined consistency models. And so rather than giving you kind of a black and white view of the world where you have hard extremes, on one end you have strong consistency, meaning you have extremely high read predictability. However, what you're doing is you're actually paying a huge latency cost. Every time you're performing a write operation, you're propagating that around the world. Versus eventual consistency, where you're going to get lightning fast performance. You'll read to the replica closest to you. However, you don't really have a lot of predictability. We allow you to have many fine click stops in between strong and eventual consistency. So bounded staleness is all about setting tight bounds on how eventual is eventual. So if you have, let's say, hard requirements, you have a mission-critical application with very, very strict RTO and RPO objectives, what you can do is you can actually control how eventual is eventual by configuring the bounded staleness. Basically, you're setting a staleness window, and if we ever exceed those thresholds, the database will prioritize replication over, above all other processes. For session consistency, we can constrain the consistency to a single session, so you're able to read your own writes within that session. Reads will follow reads, writes will follow writes. Basically, you have monotonic reads and writes. And we scope all of this within a session. And then that way, if you have, let's say, a social media application, let's say you're building the next Facebook, what you end up having to do is you navigate these hard extremes, right? If everything is strong consistency, I really don't want slow page load times because I have a billion other users liking comments. I honestly could see their like in a follow-up post in the newsfeed, but at the same time, whenever I post a comment, I should be able to observe my own comment. That way I don't have confusing user experience where if I refresh the page and my comment disappears, I'm going, hey, where did that go? Maybe I'll, let's say I'm trying to grab beers with my friend Ram, and I'm going like, hey man, let's go grab beers. I refresh the page and my comment disappears. If I go and post that comment again, let's say it disappears and I'm like, oh, maybe it didn't go through. I'll post it again, refresh. Oh, shoot, another stale read. Maybe it didn't go through. Maybe I'll post again. Suddenly, all my friends think I'm an alcoholic because I'm screaming at RAM going, let's go grab beer, let's go grab beer, let's go grab beer. With session consistency, I can save myself from that embarrassment because whenever I write that comment, when I refresh the page, I'm guaranteed that I can read my own writes. With consistent prefix, what we're doing here is rather than replicating operations operation by operation, what we're doing is we're writing this to a log and replicating the log in order. That means all of the operations, if I write operations 1, 2, 3, 4, 5, if I see operation 5, I'm guaranteed to see 4 through 1. If I see operation 3, I'm guaranteed to see 2, 1. And that means there's no gaps in time. There's also no reordering. Because at the end of the day, packets do behave mysteriously, where, not mysteriously, but they can arrive out of order based off of network conditions. And so we solve this by replicating everything based off of a log sequence number off of our log to guarantee that everything is in order without any gaps in history. Use case of this is, let's say we're now in a group chat. Not just am I trying to grab beer with my friend Ram, but let's grab everyone in this room and let's go grab beers. If I post like, hey, what time do you want to go? How about 8 o'clock? No, that doesn't work for me. 7 o'clock, OK, great. If I were to replicate these operation by operation, some of you guys might see 7 o'clock, no 8 o'clock. Other people will see 8 o'clock, no 7 o'clock. So half of the room here will end up showing up at 7, going, hey, where are my friends? Did they ditch me or something? And the other half will go, hey, why are you guys all drunk already? Like, are you, what happened here? Like, did you just start the party without me? So what consistent prefix allows you to do is make sure that all of these operations are always in order with no gaps in time. So we give you nice click stops. They're available in the Azure portal. They're not, we make it also turnkey to implement. They're just click buttons. And so we can guarantee correctness for your application with respect to consistency, as well as give you ideal performance with respect to latency and throughputs at the click of a button and make this really, really easy. Now, one of the new things we're doing with Build is we're launching a preview for multi-master. So previously, what we did was we had a model where writes were affinitized to a region and reads were made ubiquitous to all regions. Now with multi-master, what we're doing is we're also making writes ubiquitous to all regions. That means you'll get higher write availability. That 5.9 SLA isn't just for reads, for multi-region, but it's now 5.9s also for writes. On top of this, you'll get lower latency writes because you're now writing to the region closest to you, as well as you'll get better write throughput because you're now leveraging the fact that you have additional replicas accepting writes distributed all around the world. Now, it's great that we've implemented this, but also the important things are we want to make sure we guarantee correctness for a distributed system. So all of our consistency models still apply just the same with multi-master. And then one of the new things that we've implemented is conflict management. So earlier I showed you this conflict resource in our resource model. What we're doing here is, let's say I write to record ID 5 simultaneously between 2 different writers across 2 different points in the world. Well, now you have 2 different sources of truth. Which one wins? Well, what we're doing is we're actually giving you a comprehensive conflict management system where you can actually configure. Do you want last write wins? Do you want first write wins? Would you like to register a stored procedure such that if we detect a conflict, you register a body of business logic. We'll run that business logic to do conflict resolution on behalf of for you. Or we can take actually a CRDT-based approach where we understand each of the different properties, do diffing across different records. And if we understand the types and properties, what we can do is we can merge these conflicts on your behalf. So that's multi-master. So now that I have a system that is highly partitioned, highly replicated, I have many machines distributed all around the world. One of the next things is, well, then how do I deal with things like schema management and index management while maintaining availability across all of these different machines, right? I don't want to be doing alter tables, create index across such a large cluster of machines. Can we make that really easy? And this is the icing on the cake. What we do is we also give you schema agnostic indexing. And I'll give you kind of an idea of how this works. But first, what is it? What we call automatic indexing, it's a proactive approach as opposed to a reactive approach, where we will automatically index every property of every record without you having to define any kind of hints, without having you to define any schemas up front. And so what this allows you to do is if you have heterogeneous data, let's say you're doing a telemetry scenario where I have many different generations of devices. Each of these different generations of devices have different capabilities, different sensors, and therefore different properties being written. Or perhaps I just have an application where I want to just move fast. I don't want to be bogged down by doing alter tables and a bunch of migration scripts over and over. So how do I actually support this? Well, what Cosmos DB does is it implements this concept called an inverted index. Inverted indexes have actually been popular as a concept in information retrieval systems for a long time. But what we've done is we've built a data structure called the BW tree, which allows us to do automatic indexing in a write-heavy environment. It's a write-optimized data structure. And so what this inverted index looks like logically is here I have a record on the left. Let's say it's a JSON record. I have a set of properties. What we do is we build a tree representation of each of these records. The root node will be the record ID, followed by child nodes, which are the properties of that record. And I can have denormalized structures where I have nested objects, nested arrays. But then at the leaf nodes, what we're doing is we're preserving all of the instance values of that record. Now, what's cool about this is The record on the left, if you notice, it's self-describing. It's actually telling you what properties it has, what are those values, and what are the types of those values. So if I mutate this record, and let's say I have a second record come in with different properties, where I add a revenue property as well as a dealer property, what we can do is we can actually build a tree representation of this. And then what the inverted index looks like is basically adding all of these trees together. So if I merge these two trees together, I have now an inverted index. So if I run a query that says select star from this collection whose first location's country is Germany, what I can do is I can follow along that left-hand path of this tree, traverse all the way down to Germany, and that has a pointer to record IDs 1 and 2. And so what will be presented in the query result is records 1 and 2. Meanwhile, if I run another query on the right-hand side path where I go to, let's say, the dealer's property, and I look for select star from this collection whose first export's dealer's name is Hans, what you'll see here is that I only have record ID 2, because that's the only property, or the only record that had not only that value, but that whole path of values. And so what we're doing is, as you ingest records of different schemas, of heterogeneous schemas, what we're doing is we're dynamically building this big inverted index, and we couple this with our BW tree, which is a latch-free data structure to allow you to do this with very, very heavy write throughput, and be able to then index all of these writes synchronously with a write-heavy workload. With that said, just because we can index every property of every record doesn't mean you always want to. So we also give you the ability to tune this. And so this is fully a Geeks database. We expose lots of knobs and levers. What you'll notice here is on the right-hand side, I have the what's called the index policy. Every collection will come with one of these. And in the included paths, what we've included is /star, meaning index everything, and do that recursively. What I can do is I can set a set of indexed paths or included paths as well as excluded paths. And in the traditional database, what we're doing is we're whitelisting columns A, B, and C. So what you can do is you can include columns A, B, and C. Or what you can do is actually something very novel. Instead of doing whitelisting old school approach, you can also do a new way of doing this, which is blacklisting. So you include /star, and then what you do is you exclude the paths that you don't want indexed, that you know you'll never query off of. You can firm that up over time as you optimize your database. And what that allows you to do is, as you evolve your application model, 90% of the time when you change the schema, you're just adding a property that you want to query off of. So why not make that frictionless? And so that's what automatic indexing really does for you. So let's talk a little bit about the new goodies we have at Build, and then we'll open this up for a Q&A. For new goodies at Build this year, as a quick summary, we've launched provisioning throughput for a set of containers. This allows you to set RU per second across a set of containers. And what we're doing is we're co-locating those collections on the same cluster of machines such that they can actually share that throughput together. On top of this, we've introduced a bulk executor library. The bulk executor library is really there to make bulk import, bulk update, bulk delete very, very easy, simple, single methods. We have launched this library both for .NET and Java. You can find it on NuGet and Maven, respectively. And one of the nice things it does is rather than spinning up a bunch of individual asynchronous tasks for each operation, what you're doing is you're batching them up. And what that does is it makes it much lighter weight on the client side, and so you can get a 10x client side performance improvement. On top of this, we have multi-master. Multi-master is in a preview sign-up. It allows you to do writes across any number of regions, giving you better write availability as well as better write throughput and write latency. And then some of the things that we are introducing on top of this is VNet service endpoints. So as a cloud data store, what we want to do is also restrict public access from the public internet, right? Just because you have a database in the public internet, I mean, in a cloud environment, doesn't mean you actually want anyone to be able to send requests to it. Previously, what we did was we gated all of this through an IP firewall, where you could whitelist a set of IP addresses and ACL the request based off those IP addresses. That works when you're running on, let's say, VMs where you control the IP addresses. However, the big missing link was, how do I do this for PaaS services? And the answer to that is setting up a virtual network. So all of the different Azure services have been working on VNets. We're pleased to announce that Cosmos DB is now launching VNet support. And so what you can do is, this is actually compatible with our IP firewall. You can actually whitelist a set of IP addresses and join this to a VNet. And only if the machine that's connecting to it meets one of these two criteria will we allow that request go in. Otherwise, what we'll do is we'll just say, 404, I don't know what you're talking about. We don't exist. Not found. And then, of course, the last thing we're releasing at build is we have a new asynchronous library for the SQL API. Previously, our Java SDK was all synchronous operations. And what we've done is we've taken the time to actually refactor this to work with the RxJava library to build an asynchronous version of this library. And what we found is this actually gives us a 2x client-side performance improvement by moving from a synchronous model to an asynchronous model. This naturally should not be surprising since being a client-server interaction, this is naturally an IO-bound activity. But nonetheless, you get a 2x performance improvement here, as well as, since we took the time of implementing this, we also use this as an opportunity of improving the user experience such that the interfaces, we've made a much cleaner set of interfaces for this. So with this session, what we've done is we've done a high-level overview of what is this thing, understanding the resource model and some core concepts, like what exactly is a request unit, how do I partition my workload, how do I replicate my workload, and how do I configure indexing. We've covered the new goodies, and with that said, what I'd like to do is open this up for Q&A. So we have a microphone here in the middle of the room. I do encourage you to use it, or if you have a hard time, like given the seating arrangement, I can also repeat the question if you raise your hand. But yeah.
Hi.
Hello.
With all that said, I haven't seen anything regarding the storage model. Are you working directly with storage account? Is it managed disks? All the underneath of this storage model to host this amount of data.
So Cosmos DB is fully built on SSDs, and we actually build on bare metal. We build on bare metal, and that's so that we can pin our compute with a very specific drive. What we want to avoid is having ephemeral disks, which means we have to do network-attached drives. And you always have additional overhead if you're doing network requests to perform some I/O operation. So as a result, what we do for Cosmos DB is we build on bare metal. We implement all of the resource governance also on the database side so that we can take advantage of this fact. So we own our stack end to end, and we're an SSD-based system.
Okay, thank you.
Hello, thank you very much for the very informative session. So I have a couple questions. Because of the size and people coming from a traditional background of database, is there still backup and restore needed in this environment? That's question number one.
Okay, so first thing is backup restore. I'll kind of tell you both our current state as well as where we're headed. In our current state, what we do is we automatically snapshot your database, and we actually maintain a couple backups on your behalf. These are logical snapshots, and what we do is we store these in a geo-redundant Azure storage account so that we can restore them to any other number of regions. With that said, what we're doing is in our roadmap, we're actually going to improve this model so that, number one, we're going to try to remove these, well, we definitely are going to remove the Azure support process of restoring. The other thing we're doing is we're moving away from a logical snapshot to using our log store directly, and what that will do is it'll open up the doors for point-in-time restore. So much, much more narrow recovery point objectives.
So is that follow-up, is that on the portal from a user interface? People will have that capability for restore, I mean, going forward?
Yes, moving forward, yes.
Okay.
For the existing system, it is exposed to the Azure support system for the existing system. And for these snapshots, we actually automatically turn these on your behalf. We don't let you turn these off, because we also use these backups for our purposes in case should a region get wiped out by, I don't know, a earthquake or a natural disaster. Ideally, you have multiple regions set up where you can automatically fail over, but we do have users who deploy to a single region. For the users who deploy to a single region, we have a geo-redundant backup so that we also restore on your behalf to another region. So these are turned on automatically.
Okay. Question number 2, for encryption, is there any capability to encrypt data stored in the DynamoDB?
Yes.
Not that necessary.
So the good news is encryption actually is strongly enforced. All data is encrypted at rest and in transit. So when you store data, we store it at rest using AES 256. And then in transit, we enforce TLS 1.2 or SSL. We don't let you turn it off because we believe that, honestly, you shouldn't ever turn these things off. We believe encryption should be a default option.
Okay, thank you.
Hi there. I noticed about a month ago in the portal, you guys must release some changes where it'll warn you if you're exceeding your provision throughput, and you can go and click a link, it'll give you a suggestion and scale up. I'm wondering if you're going to, on the roadmap, to go to the next stage and have auto-scaling capabilities where you can provision, hey, I'll go up to 50,000, don't exceed this amount per day, that sort of thing. Is that on the roadmap?
We do have auto-scale as part of our roadmap. It is a long-term roadmap. What we want to do is we want to be very responsible, because as we dial up and down the throughput, number one is we want to make sure that we can still guarantee our SLAs around throughput and latency, as well as this also has a billing implication where if we change something up and down, we want to make sure that there are no surprises from a user perspective. So we're still thinking through of how to solve these set of problems, but this is something that we are very seriously thinking about.
Okay, thank you.
Hello. We currently use Cosmos as a DocDB replacement. If you wanted to do a large graph implementation, GraphDB, have you compared that with Neo4j on Amazon as a PaaS service?
Yes. So what we do is, for context for everyone, we have a Graph API, or we call it Gremlin API, where we've made a bet on Gremlin. So what Gremlin is it's an open source standard. If you go back even just a couple years, Graph is in kind of still an infant state where it's the Wild West. And what the Apache Foundation has done is it wants to standardize both a protocol for speaking to Graph as well as a language for how to traverse the graph. Apache Tinkerpop is Apache's answer for the protocol. Think of Tinkerpop as what Tinkerpop is to graph databases is ODBC to relational databases, and then Gremlin is to graph databases as SQL is to relational databases. We've made a bet so far on Gremlin. How our system compares is we're a scale-out system as opposed to a scale-up system. So if you look at a lot of other graph databases, relatively speaking, they're very feature-rich, but where they're a bit lacking is the partitioning story and how do you actually manage a extremely large graph. Where Cosmos DB really has positioned itself is for scale-out workloads, for massive scale graphs, where we have actually done a very good job of the partitioning and scale-out aspect for graph databases. We actually do have a session tomorrow afternoon specifically dedicated to doing scale-out of graph, and I highly encourage you to go check that out.
Thank you very much.
Hi, I have two questions. The first one is, I have the ability to disable a collection in Cosmos in case I'm using for like a dev database so it doesn't get charged with the Azure spend?
So for now, Azure Cosmos DB, it'll give you a range of how far you can dial it down. You can't turn it off completely because at the end of the day, it's not a blob store, just working in isolation, but rather it actually has a database piece of software running live for you. With that said, we're always pushing the envelope to decrease that footprint more and more. And then we also have techniques on how you can do both archival as well as hydration back into Cosmos DB, should you want to move data and do a tiering approach.
Okay. And my second question is there a way to set up an index policy to do a range scan for querying like date times? So I've had to get around that by putting it into a Unix time so that it's a number. Can I do that so that I can keep the date time in a human readable format in the collection?
I see. So yes, the technique today, right now, it's actually a matter of type systems. Today, we've made a big bet on the JSON type systems for indexing. So for date times, to do range queries, you either have an ISO formatted string where it's like year, 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 month, month, day, day, or an epoch value, the POSIX time. That's how you do it today. With that said, because we are making a big bet on open source APIs where the type system does have date time support as a data type, we also are expanding our index to support different type systems as well. So look for that as a future improvement so that you don't have to do any of these kind of workarounds.
Thank you.
Several questions. First, you are talking about multiple partitioning using the document DB. Basically, my understanding is that there's only one partitioning route can be used, right, in one connection. What exactly do you mean multiple partition within one connection? Are you talking about multiple logic names as a combination, as a partition, or this kind of mechanism to make sure the partition is equally distributed?
So Cosmos DB actually has two ways of connectivity from the SDK. One is called gateway mode, the other is called direct mode. In gateway mode, what we do is we actually proxy the connection through a gateway server, a front-end server, and then what that'll do is both route the query to the correct partition as well as a replica within that partition.
No, that's the request, but you're talking about connection partition, right? You're talking about multiple partitioning within a connection. How it is possible? Because right now, you have to set up a partition row there. So in that case, if you decide one logic name as a partition, then that's kind of fixed it.
So what we do is we actually, like I said, we have two ways of connecting. The gateway will proxy the request. The other way of routing is we actually allow you to directly connect a server to the replica. That's not on a single connection. We're actually opening up a connection for each of these different replicas. And should a partition ever split, we actually have our own protocol for detecting that. So the moment, let's say, a partition is now expanding to 2 child partitions, there's actually a back and forth dance where we'll notify the client. The client will then get the updated topology and then talk to the child partitions. And so this is all actually handled behind the scenes on behalf of the user. So from the user perspective, the collection, like all this partitioning crap, gets actually abstracted away from you as much as possible.
Okay. Second question is for right now, GraphDB and DocumentDB, when you look at the schema, GraphDB is saved as a list of the JSON, kind of list of JSON. But using DocumentDB API is not able, at least I'm not able to query GraphDB. But basically, these two APIs are not compatible.
The APIs are compatible. What you do is you actually use the 2 APIs on the same collection.
Yeah, but actually when it's saved as a JSON. It's saved a list of JSON. Is that any role plan which DocumentDB can query GraphDB, and basically these two things can be compatible as well?
It's actually saved under as an atom record sequence under the underlying persistence store. And that's actually a superset of all of these different data models. What you're referring to is you're querying this thing back out of the SQL API, so we project that as a piece of JSON. Now, what we do is we actually do co-locate edges on the source vertice. And so we also do have a set of best practices for how to choose the best partition key for when you want to interact with the same data set, both through the Graph API and the document-oriented API. We actually do have a large number of people who do this. Basically, what you're doing is documents stored through the SQL API are treated as vertices in the graph. You can annotate them with subsequent edges to do relational queries on top of traversing this graph. And then what we do is we actually have 2 different query engines. We have one query engine that's hosted on the replica itself. That's what the SQL API is talking to, as well as we have a graph traversal engine that's one layer higher, and that's what's able to do traversals across records stored across multiple replicas or multiple partition sets.
Okay, thank you.
So a question about, I guess from cost management, as somebody else was alluding to cost management. If we're dealing with, let's say, a couple dozen microservices, and rather than having a separate collection for each service, given that everything is indexed, it's feasible, it seems, to have a more generic collection where you have multiple microservices within a team perhaps sharing that collection. Just wanted to get your thoughts on that, trade-offs, and when to not do that. But from a cost management perspective, you've got all the RUs can then be kind of divvied up amongst those multiple microservices sharing that common.
I think it comes down to whether the data itself is if it's the exact same data that's being shared across the microservices or not. At the end of the day, we still do advocate combining different entity types in the same collection. And the reason why is because this gives you benefits for queries, where rather than doing, let's say, some kind of relationship, you can actually co-locate the properties across different entity types to query them back in a single network request very efficiently, as well as you can do transactions or across different types of records. With that said, there are also scenarios where you have very, very, let's say, distinct data sets that you really don't care about transactions, you don't care about coming back in the same query. And that's really what the one option is, using the new database level throughput, where you can have very separate collections that share the throughput with each other to help try to manage the cost. Okay. So if you have something like a star schema where you have, or actually not a star schema, but just different collections that sometimes this one spikes, this one other spikes, what you can do is you can actually share the RUs between these two different collections.
Hi, currently I use RavenDB, and along the lines of the, you can share the RUs across collections. RavenDB, whenever you save a type, it'll actually automatically create a container for that type of documents and split them out that way. Are there any plans of having a support for that in the .NET driver? Anything like that?
So our .NET driver actually tries to move away from this whole thought process of type, and that's because we are a scale-out database that supports multi-record transactions. So there are still benefits for co-locating different types within the same collection. With that said, from a driver perspective, it just actually views these as just records. And so you can serialize any kind of POCO. Let's say it's different types of POCO. You can serialize them, let's say you're using the SQL API, to any arbitrary JSON. From the driver perspective, it goes, as long as it's valid JSON, I can shove it into the database. And when I pull it back out, assuming you're using, let's say, .NET, it'll just use JSON.NET and go, hey, I know how I've annotated types for all of these different POCOs. When I pull it out, I can cast it to the appropriate type accordingly. So I mean, from a best practice standpoint, we still do advise co-locating types within the same collection, because there's many, many different benefits for doing so. But should you want to do, let's say, a type per collection, we're not going to block you from doing this. And in fact, some of this new functionality, like the database level throughput, really is centered around people who want to do this. Because what ends up happening is, if you create many, many collections and you end up with what looks like a star schema, what you find is one collection actually ends up having the brunt of most of your database throughput and most of your request volume. Meanwhile, you have many, many other just like smaller types, smaller namespaces that are hardly used. And what was really cool is with database level throughput is we're actually giving you the benefit of using both. You can provision throughput both at a collection level and have it shared across multiple collections. So for that one collection where you have a ton of throughput, you can give that a dedicated collection. Meanwhile, all of these other smaller collections, you can pull that throughput together.
Great, thank you.
Hi, so the rate limit is one of the challenging, right? We just handle it based on our what is HTTP core return. And with the bulk update, like everything is abstracted, like we don't even have to consider that it won't throw 4.0 or 4.13 errors.
Yeah, so basically all the transient exceptions are handled internally. So if you consider rate limiting, or you have a request timeout, or you have service unavailable, all of those are inherently handled within the bulk executor library. And anything else, so basically any non-retriable error is we leave that to the developer to handle, catch that exception and decide what to do.
Okay. And then finally, will I get, let's say, out of 1,000 records, like I have 100 failed records, do I get a summary of those 100, or how should we handle those?
Right, so again, so the one thing we catch is like if you have a bad document. Okay. So if you look at the API, we return a list of bad input documents, which are basically, for example, if you have an ID null or any such things, we don't fail the entire job. For example, if you submitted a job API with 1 million documents, we don't fail the whole API, but we just return to you the list of documents which caused that bad exception. Okay. But any of the other type of non-retriable exceptions, we basically throw an exception at that point, and you would have to catch it and retry the whole API.
Is there any UI planned to develop, like, so that I can just go to the portal and import a file?
Right, so so the library itself, native library, is more from if you want to add that as part of your core service. So something where, like, for example, periodically you want to, like, it's basically part of your service itself. But other than that, we, as I mentioned, we've integrated into Azure Data Factory. So Azure Data Factory is kind of like the go-to way if you want to have like a portal. So if you've looked at Azure Data Factory, you can actually set up a nice pipeline, visual pipeline, and all of that.
And do you have plans for bulk delete, let's say like a purge, right? So one way is like how in database we retain the schema or the table structure, just that bulk delete the data, right?
Right. So we have one, and that is in preview, while bulk import and update are GA. Bulk delete is in preview, where you can specify a SQL query. So I can say select star from C, where say C.time.
Any tentative time when that might be available?
Oh, it is like it's already in preview. So you basically, it's just that we have not, it's not part of our public NuGet. But if you look at our GitHub page, you can basically get the preview NuGet.
And
reach out to us. We'll be happy to show you how to use it.
So one question. So generally, like we are indexing on multiple fields, right? If I reduce indexing on 50% of the fields, will it be a reduction on RU's usage? Yeah. Do you have any statistics on that?
Yeah. So by default, like if you consider a 1 kilobyte document with say 12 properties or so, right? If it's a 1 KB document, we have something like a document write consumes 5 RUs, and a document read consumes 1 RU. That is the default. And as you keep the document gets bigger, the RU consumption increases, but it's not linear in the sense if you go from 1 KB to 100 KB does not mean you're going to consume 100 times RUs.
Is there any way you can do some cost estimate, like in a traditional database, I can say like this kind of operation is going to like X cost, right?
Yeah, so we do have an RU calculator online. It is a logarithmic curve,
right.
But basically what's happening is, think of this, what's happening on the underlying system. As the number of bytes grows, the amount of I/O in terms of bytes also proportionally grows, as well as the number of terms. If you have more and more properties getting indexed, we'll spend more CPU cycles generating those index terms. Now what you can do is you can actually tune the index policy to selectively index which properties you want indexed if you have many properties, let's say 1,000 properties. But with that said, I mean, the RUs is actually directly proportional to the CPU and I/O.
What about storage, per se? Would it decrease the storage?
So question for the rest of the room was, what about storage? RUs is actually purely a measurement of throughput and not storage. And so Cosmos DB actually decouples storage and throughput. Throughput is RUs per second. Storage is just how many kilobytes you have stored in the system. If you reduce the number of indexes, would it reduce the number of storage? Yes.
So on the portal, you can actually see you have a metric for both data usage as well as index usage. So if you instead of indexing 100 fields, if you're indexing 10 fields, you will see almost a 10x decrease in the index storage.
Okay, yeah, I have 2 questions. So how does Cosmos DB handle the concurrency issue? I know the MongoDB have certain kind of support. I use Mongo API with Cosmos DB. Does the same support or no?
Can you repeat the question?
Yeah, concurrency issue.
Where is the issue?
The concurrency, the application concurrency issue.
What do you mean by where is the concurrency?
So you have 2 users to update the same record.
Yes.
They have the concurrency issue. So,
so
someone may override some proposed change.
So what Cosmos DB does is it's a latch-free database and it uses optimistic concurrency control. If you look at every single record, each record has what's called an E-tag. Every time you modify a record, that E-tag value will actually update. We then use REST semantics where you do an if match. If the E-tag matches on the time of update, that means no other concurrent operation has modified that record. If that E-tag value mismatches, that means you have now detected a concurrency violation. Another concurrent operation has modified that same record. What we do is we do conditional updates on that E-tag value such that optimistically, so that way we completely remove any kind of locking mechanism, optimistically perform this update and only if that E-tag mismatch should you reject that update operation.
So, wow, it's built-in support.
Yeah.
Okay. Another issue is, does Cosmos DB support change tracking? Change tracking.
Change tracking. So we have this concept of a change feed. It's not exactly like an operation log. Instead, what we do is every time you insert or update a record, what we're doing is we have a log append structure in the backend that we're appending to, right? This is how we build the latch-free database. And so what the change feed does is actually it's a direct feed off of that log based off of that log sequence number. And so if you want to get incremental reads off of the database, use the change feed. It's a very, very efficient way of getting incremental reads from the database service. Only new records, no existing records. So if you're looking at building something like an event sourcing pattern, we actually have a ton of people doing basically event sourcing scenarios off of that change feed.
Okay, thank you. Hi. So being able to create ephemeral databases for the purposes of integration testing on like CI/CD servers, is there any plan for future support of running Cosmos within like a Linux container?
Yes. So we have a local emulator today. I think we've already Dockerized it, but right now it still doesn't work on specifically a Linux container. So we are actually working on that next on bringing Linux support for that emulator.
Okay, thank you.
Hello. Do you have any plans of releasing Cosmos DB version to run as a standalone product on premises, like SQL Server or MongoDB?
At least for now, the short answer is not at the moment. We aren't looking at that. For on-premise, we'll likely go to the Azure Stack route. The reason why is we've done a large degree of hardware optimizations where our database really makes a bet on large clusters with ample CPU cache and SSDs. And so because we've done all these hardware optimizations, we are very selective on the hardware SKUs that we support. So for on-prem support, likely what we'll do is onboard Azure Stack as part of the roadmap.
All right, thanks.
Hi. Does the SQL API support partial document update?
Does the SQL API support partial document updates? Today, no. What we do is we do blind writes. What we're trying to avoid is doing any kind of read I/O whenever we perform an update. That way, the updates happen as fast as possible. With that said, we have heard a lot of requests for partial updates, and that is something we're evaluating next. We do semesterly planning based off of the feedback we receive on the Azure feedback forums. Please do post on there. We look at that every half year, and honestly, like we're coming up on the next cycle. If this is important to you, we'd love to hear from you.
Yeah. So right now, I have to load the document and change and then put it back. That's
yes, you can either do that on the client side, or you can actually do this on the server side. And so what we've seen a lot of people do is implement this as part of a stored procedure as well.
Okay, I see.
Or you can also use the bulk so the bulk update option is where you can specify a patch document. So if you're doing it in a bulk mode, you're not doing point updates, but you have like say a batch of documents which you want to update. Then what the bulk executor does is not read the whole document and write it back, but does everything on the server side.
Okay, I see. I'll check that out. Thank you.
Can you use the microphone?
Yeah, there's some question. Does the Mongo API support partial update?
Yes. So what we do with the Mongo API is we do a layer of translation, and we do support partial updates there today. The mechanism behind the scene is a store proc, where on the server side, we'll do the read and then write.
During the keynote, there was a comment that made about a 10x savings in Cosmos DB. Do you have any information about that?
Yes. We have a publicized TCO paper. What we did was we actually used the performance benchmark that AWS did for DynamoDB, where they were comparing open source software on VMs compared to DynamoDB. We used the exact same test methodology and tried to apply that to Cosmos DB. And what we found was comparable to a comparable open source workload, it's about 10x cost saving. Comparable to DynamoDB, it's about 3x cost saving using their methodology.
So no new policy changes, just in comparison with
yeah, it was the sample workload. I mean, at the end of the day, a lot of this it depends on your workload characteristics. But what we did was they had a pretty good canonical workload that we could implement. So we went ahead and just implemented that as a representative worklow for a typical
last question.
scenario.
Can you give us an idea what's on the roadmap, say, in the next quarter? What are you guys looking at in terms of new features?
So for the next quarter, we have a bunch of things that are actually right now in preview. A lot of the big bet is GAing a lot of those. So for example, multi-master database level throughputs, our Cassandra APIs are all in preview. We fully intend to mature those into a GA manner.
Okay, in 2 quarters then.
Now you're trying to get me to spill the beans on secret sauce. If you have questions on specifics, I mean, we can talk to you in private on this.
Regarding the session consistency in the MongoDB API, because the new MongoDB API supports session consistency, but when will you support the new version of the MongoDB API so that we can leverage the session consistency in the MongoDB API?
So we're waiting for the MongoDB themselves to actually mature this. Right now they have it in a closed beta as part 4.0 in MongoDB. So today what we've done is we targeted 3.6 for compatibility. However, when MongoDB itself GAs 4.0 and stabilizes that, we'll look at ways on how to bring that also into our MongoDB API as well.
Okay, thanks.
Cool. Thank you, everyone.